Thank you very much, Professor Kazara. And I'm really, truly honored to be giving a keynote for ISCA, which is probably one of the premier conferences in computer science and related disciplines, electrical engineering, and so forth. So I never imagined I'll be in this position when I graduate from University of Tokyo, as Kazara-san said. By the way, my sister, younger sister, graduated from Waseda University, so from this university, and she's now a Sony executive. So, she's much more financially successful than I am. So maybe she made a better life choice, but we'll see. Again, I'd like to thank the ISCA organizers. It's astounding to think that ISCA has 1,280 participants. It's just wild. And 570 submissions. It's quite beyond my wildest imagination, but that's how the state-of-the-art, state of society it is today. So again, I'm truly honored. And I would be, hopefully you'll enjoy my keynote, which is both technical, but I'll try to make it entertaining. Now, when I was growing up, my hero was when in my younger days, when my high school, was Wernher von Braun, because I was aspiring to become a rocket scientist. But when I discovered computing, my hero became Seymour Cray, whom we know as being the father of supercomputing. And Seymour had left a lot of quotes, and you can find his quotes at various places on the internet. But then, when I was really proud and very honored when I received the award under his name, the Seymour Cray Engineering Award, and gave tribute. And so, but this keynote here is an extension and also evolution of the talk I gave, in that now we have massive advances in AI. And of course, Seymour probably never realized that we will have the advances in AI to this extent, but we'll try to see if his quotes that he left behind, whether we are living up to his ambitions, or was he right or wrong? And also, how are we in the light of this changing atmosphere where the architectural emphasis is now on AI and other disciplines where the metrics for the performances and other metrics we aspire for is turning out to be slightly different than we used to believe. So what was I doing when Seymour was designing supercomputers? Well, I was designing these. I was a games programmer part-time. Of course, I was doing my studies, and back then. 8-bit computer that I was programming was about running at, if he ran the Limpack and BASIC, about 70 flops, whereas the Cray 1 was running at 80, 90 megaflops. So it was like a million times difference in speed. Of course, I try to cover up the speed difference by programming in tight assembly, and this is one of the artifacts that I programmed with on the Nintendo NES system, which was 6502 system with Satoru Iwata, who later became the CEO of Nintendo. Again, I think he made a right career choice, maybe. But if you do the calculation, the physics in this game is running at a few kiloflops. So I was a very avid assembly programmer, and these are some of the things I programmed during the day. And you can find these on the internet, actually, and you can run them on the emulator, and that's exactly what I did to this screen pack capture. And so these things are running in real time, and so forth, and especially on the left-hand side, you see the Space Invaders, which, younger version of me, much younger version of me, I spent several months programming in assembly language to achieve this real-time gameplay. Fast forward tens of years. Now we have this. So this is a prompt, about a page worth of natural language prompt I gave to Gemini 2.5, describing how the game, Invader game, is played. A few minutes later, you run it on the Gemini, you get this code. And you go, and presto, we have the game. So the younger version of me who spent months in the assembly language, now tens of years later, I spent 10 minutes writing a prompt while I was at a workshop recently. And that's how things are. So that's how much advance is made with AI. Okay, so we made lots of amazing advances in AI, but is an AI a recent phenomenon? Well, no. AI has been around with us since the days of Seymour Papert and so forth, since the 1960s. And in the 1980s, Japan, in the 5th generation project, maybe some even in the audience remember, tried to build an AI machine. So already back in the 1970s and actually in the 80s, there were attempts at trying to build an AI supercomputer, essentially. These were the ICOP, so-called PIM or parallel inference machines. And when you try to dissect what they look like, right, in fact, they built about 4 or 5 types of machines, different types of machines. Each of the vendors at the time, like Hitachi, Fujitsu, respectively had designed their own PIM machines. They were all sort of a RISC-based processing elements with some macro instructions for doing then. It was all symbolic AI, things like unification. And there's some shared memory to speed up to unification. But these architectural elements sound very familiar. They had embedded network controller, electrical optical, some had electrical optical hypercube. Right? And so these were, if you look at the catalog specs, in terms of the hardware, they weren't very different from the machines we have today. What they lacked were very fast vector tensor numerics or streaming memory. Everything else was MPP. So this was about 30 plus years ago. And so what have we learned since then? That's the big question. So Seymour Cray said, if you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens? And in 1993, as a young aspiring grad student turned into a young faculty at University of Tokyo, it was the first time I attended the supercomputing conference. And if you've been to SC, they have this humongous exhibits. And even in '93, it was fairly large. It was a cultural shock. So back in 1993, there was a Cray 3. And if you know Cray 3, it was a marvel of engineering. On the left-hand side was all the parallel inference machines, which kind of looks normal, much like today's MPP. So if you look at inside, all these exotic wires and so forth. So with Cray, and also compare it to more modern incarnation, this was Tsubame 3 machine I built back in 2017 based on GPUs. It looks, if you look at technologically, it had some GPUs have very integrated wiring. It had very sophisticated memory system, so forth, coming from GPUs, but also we had a lot of engineering to do proper cooling and so forth. But still, if you look at the overall engineering, Cray 3 is much more superior. So when you look at the Cray 3 technology, it was a gallium arsenide, direct gold chip bonding, CMOS SRAM memory, immersive floor knock cooling, all these exotic stuff, which we don't even see today. Back then, Tsubame 3, it was HP NVIDIA, it was 16 nanometer CMOS, it was silicon interposer with HBM2, full bisection, but warm water. So technologically, Cray 3 was way ahead of the time, even 20 years later, compared to the machine that's 20 years later. But if you look at the performance, by all means, the Tsubame 3 was about 5 to 6 orders of magnitude faster. Now, fast forward again a few more years. This is Fugaku supercomputer, built by RIKEN and Fujitsu, with hundreds of extra thousands of people involved. And so this is a 3,000 square meter machine, still one of the largest supercomputer ever, matching sort of a hyperscaler-like scale. It has about 160,000 nodes. So when you think of now the modern hyperscalers are building these 100,000, 200,000 GPU machines, but this is, but we can build those too. In fact, we can build it much more reliably, as we'll see later. But this is was state of the art in 2020. So again, if you look through the comparison, actually Tsunami and Fugaku are not very different. So actually, from a technology point of view, the Cray 3 was much more exotic. But again, if you do the performance comparison, the Fugaku is about 8 orders of magnitude faster. And in fact, it worked. The Cray 3, then, according to the various documents, didn't quite work. So where did the gains come from? Well, first they came from with the advances in silicon. So about 10 to the 3, if you do the math or performance modeling, you get about 3 orders of magnitude increase in terms of the silicon, of course, lithography increase, also packaging, co-loss packaging, and so forth. So you get about with HBM. But also, we achieved immense scalability. So we achieved this 160,000 nodes, we're at about 16. So more than 10 to the 5, 10 to the 5th. So combined, you get the 10 to the 8th. So although the technology didn't advance as Cray anticipated, we did achieve performance gains in terms of processor, but greater performance gains were achieved by the scaling of the machine. And of course, we all know that because, like I said, the hyperscalers are buying up, GPUs by the truckloads, and that's exactly why the AI advanced. Not just high-performance computing in general, but AI advanced because of the ability to do immense scaling. So if you're applying a field, you do both, but the advances, a lot of the advances were made in the above, but also below. Now, we'll be making more advances in things like quantum. By the way, there's an inauguration of IBM System 2 tomorrow at my center, which will be tightly coupled with Fugaku. And that's why I have to leave tonight very late. Unfortunately, I will be missing this wonderful conference tomorrow, which irritates me, but that's my job. So I have to go back to Kobe to do the inauguration. But it's pretty exciting that we'll have a 156-qubit quantum computer coupled with 160,000 node machine. So, but that's exponential in terms of, in the best case, in terms of performance gains. So you get fewer number of chickens, but you're going to get a tremendous performance. Okay, so the next quote, Seymour Cray said, the trouble with programmers is that you can never tell what a programmer is doing until it's too late, meaning that it's very difficult to do something like a co-design. You can never, the hardware people, the architecture people really can't tell what the software people are doing, and the software people can't really expect what hardware is coming. In fact, my very good friend Jack Dongara says a lot of times the architects just throw machines over the fence and they have to basically program whatever that's available. But the things are much more sophisticated these days, and it's getting better. In fact, for Fugaku, with extensive co-design, we wrote this document. It took 2 years writing up this document as to what the applications are and will be when we reach exascale. So we have a 600-page doc. We wrote a 600-page document involving lots of people in the application space, and we had this whole table and charts of what are the performance requirements, what are the algorithms used, and so what are the memory capacity requirements, bandwidth requirements, compute requirements, etc. Had a huge chart, and we also set forth this objective saying that we would pick several, like 9 applications out of these 9 priority areas, like health, medicine, environment, disaster, energy, materials, basic sciences, and the goal was to achieve about almost 2 orders of magnitude speed up of the predecessor computer, the K computer. And fortunately, we were able to achieve the goal. We got about an average of about 70x across these different applications because we knew what the applications required across the board. Of course, as we know, they're very divergent in their requirements, but we tried to be, to balance the system architecture so as to be able to accommodate the needs of all applications. But as a consequence, not as an objective, as a consequence, we achieved top rankings in various benchmarks, and of course, benchmarks are representatives of different classes of applications. So, but because Fugaku was good at everything, well, most things, except AI. many things. We were able to achieve top honors in practically all the benchmarks. And also, but most importantly, we were able to build a machine that would respond to societal needs very immediately. When the machine was being built, we had the COVID crisis, but immediately we applied the machine as it was being built to solving some of the societal problems. For example, how the aerosols would be spreading the disease, which a lot of biologists had some skepticism, but we proved that this was the main case. And this actually allowed a mitigation of COVID in Japan, much more so compared to some of the other G7 nations, to the extent that we didn't have to have as stringent a curfew as other nations. But at the same time, we had the fewest number of deaths per capita. So Fugaku really helped to mitigate some of the societal crisis, and of course we continue to do that. If you go to the expo in August, you'll see some of the demonstrations of real-time detailed forecast. So so we did analysis with Hyperion Research, which is one of the consulting companies for high-performance computing. So they did an independent study. What's the societal value or the benefit or the return on investment? So Fugaku cost more than $1 billion to build and operate, but they estimate that the return on investment is 60 to 80 times more than that. So it's worthwhile building. And I guess that's why the supercomputers called attention to AI. But now with a new report, which is being finalized for 2025, with Fugaku Next, with AI, they expect more than 100 times return on investment. So this is one, so this is sort of an indirect but somewhat of a plausible explanation why many of the hyperscalers are investing so much in AI and high-performance computing that realizes these AI, because the return on these is so great. So after Fugaku, we are engaged in 3 branches of work based on our success. So we'll run Fugaku for about 10 years, which is a long time, but still, it's a pretty good machine to go, and we have every reason we should do that. But also at the same time, we are starting to design the next generation, Fugaku Next, and we've done the feasibility study until last year. And then this year, we have formally started our development, and we will do so until 29, and we'll deploy. Hopefully, we'll be in operation in 2030. And one of the big goals is to achieve a zettascale, whatever that means, at the power levels that we have today. So there are a lot of fears that AI and everything will clobber most of the world's electricity output, but we hope to contribute by demonstrating that achieving zettascale performance can be done within a realistic power budget. Of course, AI is a big target. In fact, it's not just us, RIKEN as a whole. RIKEN is a big research lab. So we have a big push towards using science for AI, but of course, these AIs involve high-performance computing. So we have this big project to propel science to the next stage, to really change how we do science using these powerful AI. And this is an ongoing project. And this is what I will not talk about, unfortunately, today, but we have also a hybrid HPC quantum. And like I said, we'll be inaugurating one of the quantum machines tomorrow. We already have a Quantinium running, and also RIKEN is developing its own quantum computer, and we'll couple it with multiple supercomputers we have. Now, with respect to science, AI for science, in practice, if you look at computational science in general, people are already using these methods. These are not new necessarily. Well, they're new in terms of like span of several years, but already people are using modern AI, which of course began with something like Google Brain, Stanford Google Brain in 2012. And of course, been propelled for the past 10 plus years or so. People are computational scientists. Because they're computational scientists, it's easy for them to adopt AI as yet another methodology to propel their science. In a lot of cases, They are using AI, generational capabilities of AI to drive surrogates, to replace or to augment simulations and things like tsunami, earthquakes, and drug design. Also, they're using the AI capabilities to drive the various designs, like the design of automobiles, and they would design automobile shapes, and then they'll verify the validity or the efficiency of the design by using very detailed simulation, which also may be augmented by surrogates. Oh, and of course, things like drug design, which are immensely complicated process. We have a team of people designing a huge pharmaceutical pipeline consisting of hundreds of components, literally hundreds of components. That are either driven by simulation or by AI or by data acquisition, data cleansing, etc. But it's still a combination of multiple AIs, multiple simulation components, like things like AlphaFold, things like GROMACS, and so forth, in order to be able to automate the design of drugs. So just like Seymour's, in counter to Seymour's statement, we learned a lesson from Fugaku, so we've been doing something similar for AI, or AI for science, by restarting the process of what's needed by a whole bunch of people who are already practicing these, and write up a whole report, which will serve as a basis for co-design. So we have this AI for science roadmap, which you can download now. There's an English version, so just say AI for science roadmap, Japan or something, on Google. And you can find these. And these cover various domains, like nanoscience, energy, life science, basic science, drug discovery, manufacturing, social science, which is still not written, brain science, earthquakes, weather, climate, disaster, space, astronomy, etc. So again, this shows that already AI is being used in practically all branches of computational science, and that people are using these supercomputers not just for running traditional simulation, but running AI workloads. In fact, even on Fugaku, which is not necessarily an AI machine, 15% of our workload is already AI. Some of the supercomputing centers that have GPU-based machines, they report more than 30%, or some centers report 40%. Of the workloads being AI workloads. So, supercomputing is the big basis for driving these modern AI, especially AI for science. But what we want to do is not just have this computational scientist, not just have the computational scientists be the benefactors of AI for science. We want the scientists in general, right? Especially people who are experimental scientists, people in the labs, people who breed mice, people who pump pipettes and those things, to also benefit from the advances in AI. So that's what RIKEN's initiative, TRIP Aegis, which we call Aegis for short, AGI for science, to basically alter or modernize the scientific process such that we would create these various models, advanced models, especially foundation models or frontier models for science, that will not only do things like surrogates or generate structures like compounds and so forth, but automate the science itself. That is to say, it will automate the process of the science from things like, from hypothesis generation, planning experiments, coding simulation codes, you've seen that AI is getting very good in coding, or it can drive robotics experiments, gather the results, write papers, critique the papers, and then archive the result, generate new hypotheses, and we're back to square one. In fact, our big objective, being RIKEN, the haven for scientists, I'm saying that our big objective is to either make super scientists, that we supercharge our ability as scientists, or if the AI gets really good, if the AI gets super good at doing science, then AI will replace us. So think the ultimate objective is to replace ourselves. So, we can all go home and AI will take over science. We can all go home and watch on the screen as science flows, just flows in front of us. And we can, or we can be in the beachside and we can sip cocktails while we watch science just being done. So that may be the future. In fact, there are already papers like AI scientists done by the Sakana AI, which is a company here, but it's an outgrowth of Google DeepMind, which already has published this AI scientist paper. So things are coming. But do you believe in a bright future where we all get better by AI? Or do we believe in a dystopian future where we get replaced by AI? So that's a very subtle question. So anyhow, but it's much more difficult. AI for science is much more difficult just because we can't just scrape the internet. We have data of varying modalities, different types of data, or omics, for example, in biology speak. And they have to be correlated. They have to be trained. AI has to be trained. But also they have to be correlated. They have to have some semantics. And because they're not linguistic, they may be attached with metadata, but they're not linguistic. So they have to have various types of forms of training that allows AI to be very intelligent in terms of being able to assimilate all these data and make some, do some reasoning, because now it's the days of reasoning AI. The other difficulty is that these data are massive. So if you scrape the entire internet, it really doesn't amount to much if you look at how much data is being used to train the commercial AI. Even though they are frontier models, they are in terabytes, or like if you take an image, hundreds of terabytes, maybe up to a petabyte. But any of these data, scientific data, can be more than a petabyte. Right? And also, if you look at an image, if you look at an internet image, let's say you're training a multimodal model, you have an image, a typical image on the internet, maybe like HD, 2000 by 1000, very modest amounts of data. But if you take a look at what scientists are requiring in terms of data, even if they're like 2D, the modern instruments have immense resolutions. So if you take a CT scan, a slice of data, these modern instruments can be like 100,000 by 100,000. So there are 10,000 times the data. Each of these images can be terabytes. And it can be 3D as well. And if you know how these transformers work, if you try to process these using visual transformers, you really can't, because the input context needs to be a terabyte. But if you know transformers, no transformer out there has an input context that can handle a 10,000 terabyte token. So what do you do? Okay, so one of our AI teams, a very bright guy, Mohammed Wahib, he and his team had devised a way using classical supercomputing or HPC technique to use hierarchical, quad tree segmentation that allows them to go from n squared complexity to n log n by using quad tree and some sort of a space filling curve. Again, very classical typical technique used in HPC. By applying that to images or visual transformers, they can greatly reduce the complexity. And coupled with more recent advances in being able to handle very large input contexts like ring transformers and so forth, they were now able to process these very large amounts of imagery data from things like cancer tumor cell pictures to very detailed atmospheric data. This is in collaboration with Oak Ridge, and so forth. In fact, the results could be quite science fiction. So what the team is now doing is to work with people at Duke University and also with Oak Ridge and also Kyoto University and so forth to get the 3D image of a brain at 5 micron resolution. Now, with various advances, you can get down to that resolution. And this allows you to, with very advanced segmentation, analysis, reconstruction, and segmentation. Again, using the method I mentioned, you can reconstruct the neuromorphic synaptic connections between the neurons. That is, you can get the program of the brain. Now, on Fugaku, we already have a brain simulator that allows you to simulate the entire human brain. And in fact, actually, we're displaying that at the Expo 2025. So theoretically, we can scan the brain, capture the neuromorphic connections, and we can reproduce the functions on a supercomputer. What's that called? Well, it's brain uploading, which is like science fiction, but of course we haven't done that yet. But it's now in the realm of possibility that we might be able to upload brains into cyberspace. Of course, we'll try that with mice and so forth. Humans are still a way to go. But maybe immortality may not be so far, so outlandish after all. Another real time. So if you look at a lot of the roads, depending on the country, of course, but you get lots of deterioration. This is a multi-billion, in fact, trillion-dollar industry trying to trying to maintain these infrastructures. And so what we want to do is to use the most advanced instruments, like what we have at RIKEN. We have a spring-gate light source, synchrotron light source, which, by the way, if you look at the picture, it's hard to grasp, but that's like a kilometer ring. Okay? This is out in the mountains of Hyogo Prefecture. It's about 70 kilometers from our site. But we're by the seaside. They're up in the mountain. In fact, what you see in the middle is a mountain. So I asked, why did you build a ring around the mountain? Well, the director said, well, that was because it was very convenient. It was circular around the mountain. So what do you have inside there? He said, nothing, it's a mountain. Okay? That's a small mountain. And they also have a linear, this long part that's the linear accelerator, that's X-ray-free accelerator. So actually we have two light sources, one X-ray and one X-ray-free. So anyhow, this Spring-8 is one of the world's premier light sources. And what a light source is, basically it's like a huge microscope, okay? It's like a huge electron microscope. So what it can do is to take those samples and do very, very detailed analysis, like 10K by 10K by 10K reconstruction, captured images, but the resolutions are getting higher and higher with the advances of sensors. So we needed ways to be able to take those samples and do this reconstruction, segmentation, and analysis. And these are all supercomputing jobs, because each of these images are terabytes in size. Each one is terabyte. So we came up adapting some of the stuff we did for that. You get an image like this. This is like a cross-sectional scan, but we can do a full 3D reconstruction. And now the scientists regarding these that study these road deteriorations, they have novel insights, because never before they were able to really capture what was inside, but now they know exactly what's happening. Okay? So now they're working to correlate the structure here, so they would take a sample and determine the overall deterioration of the area, such that they can recommend and pinpoint and recommend places that need repair, what type of repair versus what areas do not need repairs yet, and they can be very efficient about that. Okay, so and there are many, many, many examples like this being worked on at RIKEN and our partners. So we'll augment, because we need more AI power, we're augmenting our Fugaku. I said we'll augment that with our quantum computer. Quantum computers are not yet quite ready for production AI, so we're augmenting Fugaku with traditional GPU-based cluster. This will be a mid-sized cluster, several thousand GPUs, but it should be very effective. And also working with our partners, for example, with DOE, we signed an agreement, also with Oregon National Lab, to work on AI science. So, our machines, we know what we're, counter to what Seymour said, we think we know what we're doing, what we need, and I'll get back to that later. Now, so based on all these sciences, we need to be able to design systems. So not just chips, but we need to design systems that are capable to handle this workload. Because as I said in my beginning, it's not just about the chips and the architecture at the chip level, but also the reason we have such immense capability with AI is because we could scale out our infrastructure. But that obviously presents whole sets of very difficult problems. So Seymour said, anyone can build a fast CPU. Well, I don't think that's true, but that's his word. The trick is to build a fast system. With that, I agree with. Okay? So then the question is, will fast HPC systems converge or diverge with AI? So that's exactly the question we're trying to answer with our Fugaku Next. So we were running our feasibility study from 2022 to 2024, and this was being led by Masaaki Kondo, and also I was his advisor. And we were working with this time, very different from Fugaku, where it was mostly Fujitsu working on the machine. This time, we were, from the onset, we were involving the usual suspects, like US usual suspects, and some, well, you can regard ARM as being somewhat European, somewhat Japanese, somewhat US, but nonetheless, what you see here looks like a sponsor logo, but they really seriously worked with us and really appreciative. So everybody came up with a strawman architecture of our machine circa 2029, 2030. And and they came up, and the numbers look very similar because people are working on very similar roadmaps, like HBM roadmap, lithography roadmap, and so forth. Now, so of course the numbers were heavily emphasizing AI performance. So we're very happy when we work upon very detailed studies with them. There's a projection that we can likely achieve somewhat zettascale, what you might regard as a zettascale performance in terms of very low precision arithmetic with some optimization like sparsity involved, which is great. And this will be under 40 megawatt. This will be under 40 megawatt power limit. Okay, but for HPC codes, we're seeing, for example, memory bandwidth. Fugaku is about 160 petabytes per second. But on this machine, we anticipate somewhere around 800 petabytes per second. So that's only an increase of factor of 5. So, and similarly, other parameters, when we analyze them, we achieve the overall numbers we came up with. If we don't change the algorithm, if we don't change the code, then we can only achieve 5 to 10 speed up. So, but we got together and considered, can we do more? And that really leads to the convergence. So if we look at the various elements, the compute, memory, network storage, but also there are algorithms and programming libraries. So we have to think of all these elements holistically. We can't just focus on one thing. We can't just say we have a faster CPU. We can't just say we have a faster memory. We can't say we have faster storage and so forth. We have to look at each of the elements, but also how they correlate to see if HPC codes can be sped up. Traditional HPC codes can be sped up. So to that extent. So firstly, when you look at dense linear algebra, which is used in about 30% of our applications, like things like density function theory and so forth, material science. So the trend has been to emphasize low precision matrix multiply and have less emphasis on the high precision matrix multiply. And so, for example, NVIDIA, going from Hopper to Blackwell, basically took away the high precision matrix engine. So that's why their vector and matrix performances are the same. So is this good or bad? And some people in the HPC application community says it's a bad thing because that takes away FP64 computing. But firstly, from an architectural standpoint, this makes every sense. And I don't think I have to preach the choir too much because I believe the audience is here well-versed in computer architecture. But when you think of, basically when you think of the surface to volume, it doesn't really make sense to have a very large function unit with a very low, in relative terms, very low interconnect between the units. So most of the energy is used by the compute units and not by the transmission between the arithmetic units. So it really doesn't matter if it becomes a matrix unit or just you handle with a vector with a register in between. Okay, energy-wise, it doesn't make that much difference. Whereas for low precision, it makes a lot of sense because the volume here, especially like 4 bits, the compute is trivial. So most of the energy is being wasted by the interconnect between the arithmetic units. So what do? Well, you pack them together as much as possible and thus historic arrays. So it makes every sense it's very wire energy efficient to create a low precision matrix multiply, whereas it makes very little sense to create high precision. And that's why the GPU vendors have been emphasizing this, and of course, because of the AI demands. Okay, so what do? Okay, so given this reality, what do you do? Well, so deep learning, yes, low precision, but now there are a slew of numerical techniques that allows for the accommodation of high precision, not at the loss of FP64, but in modern architectures, it's actually faster to use these low precision units rather than to use the high precision by various numerical techniques such as mixed precision and emulation. So first, mixed precision. This slide I borrowed from Jack Dangara, my good friend Jack. And so mixed precision is to use low precision as much as possible for expensive operations, and to, when needed, use high precision in mixture. And you can use techniques like Newton methods, to essentially recover the precision. I won't go into numerical details, but basically it's a fairly simple formula. And you can apply it to various things, mostly for things solving system linear equations. And that's what most of these dense linear algebra simulations do. So basically, you do order n cubic operation in low precision, whereas FE64 precision is order 1 or order n squared. So most of your expensive operations are being done in low precision, but you get exactly the same result, sans a few caveats. So what are the results? Well, there are various results, but the latest is the latest what's called HPL-MXP, which is like a benchmark for these mixed precision arithmetic. And you can see that, that one of the 4th ranking machine, AIST's ABCI machine, which is a 3rd generation. I was one of the designers for 1.0, but my friends at AIST had succeeded, and they now built the 3.0. If you look at the HPL-MXP flop versus HPL, this is computed purely FE64. This is computed using mixed precision. Again, you get the same results, sounds pivoting, but it's 16 times faster. Okay? So this shows that with the use of, if you use the appropriate mixed precision, you can be a lot faster. So that was a system of equations, but what about other things? Like if you just trying to do simple matrix multiply, then you can't use these Newton's techniques because you don't converge the solution. So then comes the emulation scheme. That is, you try to emulate high precision arithmetic using these, for example, matrix engines or tensor cores. Now, this Ozaki scheme is a hot topic in the HPC community. This is Professor Ozaki. He was the original inventor. Now, the Ozaki scheme 2, just published, which is really a Ozaki Imamura scheme. Imamura-san is one of our PIs at my center. And so basically, again, I won't go into the math, but basically you try to do the emulation, right, of using integers. And on the Grace Hopper, you can actually get faster. Again, even on Grace Hopper, which has a tensor core, FP64 tensor core, using Ozaki scheme, you can get faster math by using emulation because the integer units are so fast. Even if you lose factor of 20, 30 by emulation, you still are faster than hardware. And we project that moving forward, when we go to something like 2027, like Rubin 300 Ultra, okay, the DGEM using FP64 will be at best 100 teraflops on this four reticle side GPU module. But we can expect to get somewhere about a petaflop in emulated FP64. A single chip petascale chip in FP64, which is pretty amazing. The first time the petascale was achieved was with Los Alamos National Lab Roadrunner. That was a whole supercomputer, and that was back in 2008. Tens of thousands of chips. Now you can do it with a single package in 2027. That's our projection. What about numerical precision? Well, so this is being worked on by some of our application teams in collaboration with system team. This is William Dawson, also works with us, and Jens Donkin, who's our performance and benchmarking PI, and they've done analysis of these DFT codes. And they say the performance is actually not only sufficient, but also it can go to low precision, which further enhances the performance. So what about sparse linear algebra? So if you don't change your code, our recent work shows that you don't get much advantage. So you only get maybe 30% increase by the use of tensor cores. So you really have to change your algorithm. But how? So work being done by Ichimura and Ichimura's team at University of Tokyo Earthquake Lab. What they are doing is to notice that when you have certain types of code, for example, earthquake code, and you're doing wave propagation, your structure really doesn't change much because usually when you have this FEM codes, things change, so you need very large degree of freedom in your coefficients. But in wave propagation, you don't because things don't change much. So they said, well, they can have the integer, they have the coefficients limited to integer range. In fact, int 8 range here, like here. So then they can start using tensor cores. So they got enough compute. So it's not so much they get speed up by the tensor cores themselves, but they get speed up because they reduce the amount of data being transferred from 64 bits to 8 bits. So achieve 8 times speed up, okay, by this method. Or actually more than that. So that's one way. The other way, this is being worked on by Professor Iwashita at Kyoto University. What they're doing is to use preconditioners to limit the range of the coefficients. So previously, preconditioners in iterative methods have been used to, for example, reduce the number of iterations. So that's been the objective function. But now their team is using the preconditioners with the objective function of limiting the range of the coefficients. And with that, they can start using integers again, or very low precision numbers, and thus allowing them to greatly speed up because they get advantage, again, in terms of memory bandwidth reduction. And you can test all these using all these tools that have been developed by our system team that allows you to flexibly change the precision in your code. And also, in the future, we believe that all these code changes can be driven by AI. One important thing I must mention is, Seymour Cray said parity is for farmers. So why does Fugaku work at all? Okay? So Fugaku, during the 5 years of operation, we only see like 2 to 3 nodes failures per week over 160K nodes. And that's about 10 to the minus 7 failures per node hour. So Fugaku is an ultra reliable machine. But this is sort of a fit rate you require to be able to run 10,000, 20,000, 50,000, even 100,000 node scale jobs without failure. And this has been built in as a system, right? So it's not just the processors, the interconnect, the software, not just the failure avoidance features, but also failure recovery features, are all built in. So that's why the job completion rates in Fugaku is amazingly high, even though many jobs involve thousands to tens of thousands of nodes. Now, this is a paper by Meta. It says the failures, well, it's a little apples and oranges comparison because they also have some of the software failures. It's about 10 to the minus 4 to 10 to the minus 5 failures per node hour. So it's about 3 orders of magnitude lower. So the job failure rate is about 23%, which is, for Fugaku, is unacceptable, despite the fact we have a much bigger machine. So resiliency is critical, because large AI training runs. Well, it's not easier to I/O, but still, because the demanding checkpoint is smaller than standard HPC job, but still, it's very, very demanding. And we really want, also, it's critical for modern AI, where guaranteed real-time response via inference is essential. So why is that? Well, because it's very simple. These resilient features have been built in the chips and the system from day one. So that's where Fujitsu did the best job, in our opinion. They put mainframe-grade RAS in the chip. And also, in the interconnect and other places, they built in all these resiliency features. And also, not just in terms of the original design, for example, we found HBM found to be a major source of transient errors. So what we did was to do aggressive ECC scrubbing to correct errors before they turn into double failures at millisecond intervals. So we were afraid that this will lead to significant performance degradation, but actually performance penalty was about 1%. So we said totally acceptable. Also, the interconnect has all these resiliency features built in. Yeah, there are many others. So, and there were Rust system software, so preamble, monitoring, detection, fast checkpoint. So this says, of course, from a research perspective, it's great to design these novel hardware, but to build a real system. Resiliency is one of the most demanding features, especially in the days of these large-scale AI. Otherwise, your system will not work, and I can guarantee you that. So parity is farmers, but since farmers buy a lot of computers, I think parity is for farmers. Right? Interconnect, and I think I'm running out of time, so I'll go quickly. But interconnect is also very important, and or interconnect friends actually know this, but just to repeat. But just to debunk the myth that some of the people typically say that compute-bound applications like DFT, for example, does only algebra, so it has correlation with link-back, so network doesn't matter. Whereas memory-bound applications like CFDs, some are studying algebra, so that correlation with things like HPC and Graph 500, so it's bandwidth-bound and network-bound as premium. Actually, these are completely false statements. Because when you think about it, most dense linear algebra jobs are strong scaling. Okay? So that means interconnect actually becomes a premium. And we now come to realization with this. And many of you know says, oh, that's obvious. But what's obvious now was not that obvious to many people. We now know it's obvious because we have the scale-up network in AI. And that's exactly why people want AI as a scale-up network. Have a two-tier network, scale up and scale out. And because most AI jobs, especially tensor parallelism, is strong scaling. Okay? Are there HPC jobs that require strong scaling? Yes, dense linear algebra, and some of the other things like spectral methods also require strong scaling, because they're based on FFT. So scale-up networks are not only beneficial for AI, but also very beneficial for HPC. Okay? I'm going to finish in a few minutes. And also, a similar analysis can be done for sparse linear algebra. Actually, sparse linear algebra, network really doesn't matter, counter to many people's beliefs. So you can have a good scale-out network. As long as it's a reliable scale-out network, it's fine. So in terms of the network, interconnect is very likely that AI needs and traditional HPC needs will converge. Now, what's happening in total? Okay, so when you look at the some analysis report that just recently came out, good news is that we're getting even higher density matrix multiply in future generation GPUs and beyond. Okay, just for the next generation, but also beyond, which is great news, as I said. Also, scale-up world size is getting, of course, there are lots of arguments as to whether this will persist in the future. I won't go into details here, but largely scale-up being scaling out to scale up is good. But the bad phenomena is the TDP is going up, but the memory bandwidth is also, it's only growing linear. So compared to Fugaku, bytes per plot, bandwidth per watt is not increasing. Okay? It's not increasing. So this is something I call out to the architecture community. You've got to solve this problem. Okay? We're also trying to solve this problem. I can't tell you because it's under NDA. But innovation in memory is the most important factor in the future of high-performance computing, including AI. It's the most important thing. If you say single subject matter, that's the most important thing. So combining all the techniques, we hope to achieve a few hundred x. Of course, for AI, that's it, but for also simulation, we hope to achieve a few hundred x over Fugaku. So both for AI and HPC, we hope to achieve that scale within 40 megawatts. Final words. Okay, but this is an architecture community. And so I got to say, so I got to pose a question. Specialized architecture, do they have a future? So there will be an upcoming article. Actually, we are writing, but finalizing. And basically, the article suggests that heterogeneous, macro heterogeneous architecture is the way to go. But if you have specialized architecture, what about the algorithms? What about the software development? What about utility and generality? What about maintenance and services? What about resilience and reliability? That's all. In fact, this has been a classic problem. And that's exactly the reason why there's a graveyards of these specialized architectures. There's a homepage, the Supercomputing Society. So looking at it, you know that specialized architecture failed, mostly because of software. Oops. But is there a hope? So I asked the AI again, Gemini. And with AI, with automated programming, automated hardware synthesis, and so forth, I believe there's a future. Now, AI-driven, so you have modern AI coding, novel HC ModSim, AI algorithms. You have jumble of work on customized HPC architectures and their auto-generation. But what I found was that the crossroads of all these, there's not much research. So there are lots of research here, or here, even here, but the crossroads of using AI to generate co-designs for hardware, software, for these customized architectures, so you can take any algorithm, generate both software and hardware automatically. It's not there yet, okay? But there's hope. And I think that's where you can be unique. And that's what Seymour says. You always have to do something different. He said it before Steve Jobs. And I hope that's where the architectural community will go with all these tools, all these innovations, with all these analysis, that we will lead to a better future due to the fact that we have all these, we have the architecture community basically was a ground basis for these advances in AI. Now it's for the AI to contribute. Okay. Finally, we got 1,200 people. So I hope you'll come back in January 2026. There will be a big conference, 3,000 people, hopefully, in Osaka, HPC, called it HPC/SC Asia. Can I wear this kimono here? And this will be a big amalgamation of HPC, high-performance computing, hardware, software, and everything just like SCISC. So I hope you'll join us January 26th and 29th. In fact, the workshop calls are already out. Deadline is the end of this month. So if you're interested in new architectures for HPC AI, then you can submit a workshop proposal. Okay? Thank you very much.